Hello, Heritage Academy Geometry students, and welcome to another awesome edition of Geometry, Seeing, Doing, Understanding. For this video lesson, we're going to cover lessons 4.2, Polygons and Congruence, and lesson 4.3, Angle, Side, Angle, and Side, Angle, Side Congruence. In order for two objects to be congruent, we already have learned that they need to have the same size and the same shape. This idea of congruency is particularly important in our future studies in geometry, so we're going to dig deeper in Chapter 4 to understand how congruency applies to different concepts in geometry. As always, let's talk now about our ultimate and intermediate objectives for these lessons. So a famous Christian author actually talked about congruence in terms of how we live our lives versus how Scripture says we should live our lives. And he stated, the Christian life is the lifelong practice of attending to the details of congruence. Congruence between what we do and the way we do it. Congruence between what is written in Scripture and our living out what is written. Congruence of the Word made flesh in Jesus with what is lived in our flesh. I just really liked how this author, his name is Eugene Peterson, and this is from his On Being blog, and it dates back from December 15th, 2017. I just really appreciated his ideas of congruency in our spiritual lives. So I hope that this is a guide for you as we study congruence in shapes. Now, more specifically for this lesson, we're going to define polygons and congruence. We're going to use the correspondence of lines and angles to identify congruence. We're going to use mathematical notation to represent congruence. And we're going to study postulates for angle, side, angle, that's what ASA means, and side, angle, side, SAS, congruence. Let's expand our previous definition of a polygon. So a polygon is more than just line segments that are bound by a plane. If we want to be very specific and precise, we should say that a polygon is a connected set of at least 3 line segments in the same plane, such that each segment intersects exactly 2 others, one at each endpoint. So let's take a look now at what this means. If we say that A, B, and C aren't just points, but they're going to be endpoints for a polygon that we want to make, then we would want to connect those endpoints with line segments like so. And this makes a basic triangle shape. Now let's review what we can say about this shape. So our line segments are line segment AB, which can also be expressed as BA, line segment BC, and also line segment CA. We can also talk about the angles that are created where those line segments intersected. So angle A, in this case, can also be called angle BAC or angle CAB. And same goes for angle B and angle C. You can see the multiple ways to name these angles. But more importantly, make sure that if you're using your 3 letters to name an angle, that your vertex of the angle goes in the middle. Also, don't forget to use your mathematical notation from here on out when we're working these problems out on paper. Here's a display of some simple polygons with which you're familiar. Now, what conclusion can you make about the relationship between line segments and vertices or angles in these simple polygons? Well, let's start with the triangle. How many sides? 3. How many vertices? 3. Coincidence? I don't know. Let's look at the octagon over there in blue. How many sides? 8. How many vertices? 8. Are you starting to figure out a pattern here? You probably are. And you're correct if you're thinking that the number of line segments in our polygon equals the number of angles or the number of vertices. So that's one of our guiding principles as we move forward for any polygon. So now that we've explored the definition of a polygon, let's look at some other figures and see why these are not polygons. So a circle, an oval, any shape like that is not constructed strictly with line segments. So anything with a curve in it or that's completely rounded is not going to be a polygon because it doesn't fit that definition. Here we see a figure that's not completely closed off. Polygons need to be completely closed off. All of those endpoints need to have a connection. And also here, we have lots of line segments. Everything looks closed off, but now we're having an issue with where our line segments are intersecting because we have some line segments that are intersecting at more than one endpoint. So none of these three figures here are polygons for those reasons. It's also worth noting that there's something called a regular polygon. And a regular polygon is when in that particular polygon, all of your sides have the same length and all of your angles measure the same degree. So an equilateral triangle is a really strong example of a regular polygon because all sides are equal in length and all angles are equal in degrees. You can see several other examples of regular polygons in this image. So if I want to talk about polygons and their congruence, or if I want to show that they're the same size and shape, then I use different types of notation to do that. So notation is going to continue to be a theme throughout this lesson. So if I want to say in these two triangles that BC is equal in length to EF, I can use one tick mark to show that, and we just call those little lines tick marks. But if I want to show that AB is equal in length to DE, I'm going to use two tick marks instead of one because I already used one tick mark to show my other lengths, and those lengths are clearly different. AB appears to be quite a bit longer than BC. Now, you're probably noticing a pattern here, and you're right if you notice that we just keep adding more tick marks if we have different lengths of sides. And we see that AC looks like it's actually longer than the other two segments. So we're going to put 3 tick marks on that. But if we also put 3 tick marks on DF, then we're saying that AC equals DF. Well, if BC is the same length as EF, we can also say that BC is congruent to EF. They're the same length. So to show congruency with mathematical notation, we're just going to make an equal sign with kind of a tipped over letter S. We could also say that BC corresponds to EF, and we show that idea of correspondence with that arrow in between them pointing both ways. We can do this for all of the sides in these two triangles as shown. We also have mathematical notation to show that angle measurements are equal. So if I'm using my same two triangles, but this time I want to talk about angle measurements, if I want to say that angle A is equal to angle D, then I'm going to use kind of these rounded tick marks, which we could call arcs. And I could say then that angle A equals angle D. But if angle B is a different amount than angle A, I wouldn't want to just use one arc. I'd want to use 2. So if I want to say that angle B is equal to angle E, I could go ahead and use 2 tick marks to show that. And just like before, you may be noticing a pattern. We're just going to use 3 arcs to show that angle C is equal to angle F. And just like before, we can say angle A is congruent to angle D and that it corresponds to angle D. So we can do this for all of our other angles as well. So just different ways to talk about the same concepts here. In order to determine if two polygons are congruent, we don't always really need to know every little detail about them. We just need to know a few things. And this leads us to our first postulate for this lesson, and that is the angle side angle postulate, which is abbreviated ASA. And this postulate states that if two angles and the included side, meaning the side that's in between those two angles, are equal to 2 angles and the included side of another triangle, then these 2 triangles are congruent. And you can see from this picture here, if we're saying that angle B is the same as angle Y, and that line segment length of AB is the same as XY, and angle A measures the same as angle X, then we have congruent triangles here. And let's look at these one more time and remember that ASA just means angle, side, angle. Now let's look at these triangles. Notice that they're in totally different positions, and yet we have two sides that have the same tick marks and an angle that have the same arcs, which indicate there are congruent sides and at least one congruent angle here. And this brings us to a second postulate that we're going to explore throughout this chapter, and that is the SAS, or the side angle side postulate. And this states that if two sides and the included angle of one triangle are equal to two sides and the included angle of another triangle, then the triangles are congruent. So there's another look at those triangles, and even though they are in different positions, they are still showing that they are congruent by the side angle side postulate. There are many more things that we're going to cover in terms of congruency this year. This is just meant to be a little bit of an introduction. But for now, just continue to remember that congruency has to do with same size, same shape. And we'll explore these concepts more in class, where I will see you soon.